So we mentioned that solving this equation or we wrote this as, no, that's the way we wrote it. So solving this equation will tell us the orbit of these objects. So M2 rotates around M1, the object of mass M1, and vice versa. So we want to figure out what that orbit looks like. And so we have to solve this equation. So it's a little tricky, but there's a sort of a standard process. So we note that we figured out this constant of the motion, right, this h quantity. And then to solve this equation, it's standard to replace this variable with a variable u, where u is 1 over r. And so h then becomes theta dot over u squared, given this. And let's try to replace this with u, because it's easier to solve the equation in terms of u. So we have, so r dot is minus 1 over u squared du by d theta dot. And that can be written in terms of h as, right, so notice I'm just taking derivative of r. So r is 1 over u, so I'm taking the derivative of that with respect to theta, and so I get minus 1 over u squared. Right, because r is u to the minus 1, and then taking derivative of u and then theta with respect to t. And now I'm trying to write this in terms of h, so I get minus h du by d theta, because this is what h is. So it's this divided by that. So I have minus h du by d theta, and r double dot is, so we're taking derivative of this, but the h is a constant. So I have minus h second derivative of u theta dot, which is, so we have minus h second derivative of u and theta. This then becomes h u squared, and so we can write this as minus this constant squared, u squared second derivative of u in theta. And so this equation becomes minus h squared u squared, two derivatives in theta of u, minus theta dot squared over u equals minus g m1 plus m2 u squared. Theta dot squared is equal to h squared u to the fourth. And so we get minus h squared u squared d2 u d theta squared minus h squared u cubed equals minus g m1 plus m2 u squared. And ultimately simplified to, let's get rid of all these minus signs, two derivatives in u, theta plus u equals some constant, gm1 plus m2 over h squared. Okay, so that's the thing we have to solve. And the solution is right, two derivatives proportional to minus u plus a constant. So the solution to that, which we can check, is u equals, there's going to be a harmonic function, a cosine function, m1 plus m2 over h squared, or sine function. 1 plus, usually the solution is written in terms of the constant here is some e, cosine of theta, that's a function of theta here, minus some phi, some initial, some phase, initial phase value. So that's the solution. So you can take two derivatives of that, where we can check that this satisfies this equation. Taking two derivatives of that in theta, we'll just get minus sine times cosine back, and then we have the function itself and a constant. And we can check that this function, in fact, obeys that. Right? We take two derivatives of this, and everything else just hangs out, goes along for the ride. Okay, so let's explore this. Well, first of all, let's write this in terms of r. So, right, we want the radial value, which is the distance between these two massive bodies of mass m1 and m2. This becomes h squared over g m1 plus m2 times 1 plus e cosine of theta minus phi. Right, we could plug in theta. Of course, it depends on what these values are. These could have different quantities. We'll explore that in a second. Let's see, if cosine, so this thing can be 0 for some values. And then for those values where this is 0, we can call that r, I don't know, r naught. And for values where this is not 0, then we'll have values of r which are greater than r naught, and values of r which are less than r naught, right? This could be negative. And so we're subtracting from 1, where in other words, r naught is, then we can call h squared over g m1 plus m2. I'm not sure that's terribly useful. Maybe it's better to notice that there's an r minus, or there's the smallest value that we can have for r, which is h squared over the constant times 1 plus e, right? Because this thing, the smallest it can be is minus 1. And so, plus, we want this whole thing to be as small as possible. So we want to add, so plus 1. And so this is 1, and so we add e. And so this is, the r is as small as it can be in that case, and we can call that r minus. And then we can look at an r plus, and that would be an h squared over g m1 plus m2 times 1 minus e, right? So when we use the minus sign, take the minus 1, the lowest that this can be, the smallest that it can be, then we have 1 minus epsilon. So notice that epsilon cannot be it has to be less than 1. So there are solutions where this thing lives in that space, and when that's the case, it's actually an ellipse. So in other words, we have one of these objects here, m1, and then we have m2 can have a value which is what we called r minus, the smallest possible value, which is this, and then it can have an r plus, the largest possible value, an r plus, and then everything in between. And this kind of thing is an ellipse. Not the only solution to this. Of course, if e goes to 0, then it becomes a circle. But that's only possible as the mass m1 dominates over the mass m2. So we've shown that an ellipse is a solution to the equation of motion.